Hi everyone, I'm Prateek and we have been discussing about transformers. We have already studied about tokenization, embedding layer, positional encoding, and now we are going ahead on understanding how attention works. So just as a quick, very small revision, we'll just do what we have studied. So for example, there be a sentence called I am happy, and I'm using word based tokenizer again. This is only for simplicity of everything so that we can understand things easily. So I am happy is one sequence or one sentence for now, and then it converts gets converted into tokens. So now we have three tokens, which is I is basically, let's say, 31. I'm just taking some random examples. This become M becomes 22, happy becomes 59, just for example. Okay, now these are tokens, so we know, okay, this is tokenization. That is tokenization. This part from converting a word into numbers is tokenization, and I'm using word based tokenizer. After this, there is something called as embedding, which basically implies that every word will now get converted into 512 dimension vectors to basically represent each word in a vector space where closer words are nearby to each other. So for example, 31, which is I, is represented as 0.09 comma 0 point something 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 till 512 dimensions, comma. There is this other word, comma. There is this other word. Okay, so I is now a 512 dimension vector, M is now another 512 dimension vector, happy is now again another 512 dimension vector. After I have converted this, now again this is called embedding. So this process of converting tokens into a vector space is called to embedding. Then we studied, so embedding has captures meaning. Embedding layer captures meaning of the words. Next thing we do is called as positional encoding, which basically is to capture position or order of the sentence. Okay, because words at different position may make sentence mean in a different way. Okay, so now positional encoding. Now what positional encoding do is for every single dimension, for every single word, for example every single dimension in every single word, which is represented by 512 dimensions. Now positional encoding, for every even position will apply a sine formula, and for every odd position it will apply a cos formula, and will then generate another vector. For example, let me draw that positional vector by uh, another 512 dimension vector. For every word it will be a 512 dimension. I'll just scroll this so that it is visible. Right, so now every word has a 512 dimension vectorial representation. This is positional encoding. This is, let me call this PE, positional encoding. This gets added up to the actual words so that their order is now combined with the meaning. So order plus meaning we are combining, which basically means we are taking this. I'm just taking this copy, and then we'll paste it here. Okay, so this is what, this is our vector, actual vector. Now this gets added up, so this gets added to this gets added to this gets added to this, okay, which generates a new 512 dimension vector representation okay, which has generated a new file which now contains meaning plus positional encoding. Now that we have captured meaning and positional encoding, we'll move on with something called as capturing contexts, which basically means every word is reference to another word. Let me draw this with a yellow color, for example. So this context is related to capturing is related to context. For example, if a sentence was I am happy, this basically means that every another word would be linked to, so I is linked to am, I is linked to happy, M is linked to happy, M is also linked to I, happy is reversed linked to M, happy is reversed linked to I. So I has some impact on M has some impact on happy. Now these could be high impact, low impact based on their relation. So what I want is, I want a table. Before I understand what attention does is, basically what do I want when I talk about attention? So I want attention of every one token or one word on every other word, which basically means what is my relation with I to I, what is my I is, how is my I related to M, how is my I related to happy, and I'll try to give it a number. Okay, I'll try to give it a number, and bigger the number, more higher is the impact. Same way, how is my am related to I? Okay, how is my am related to M? How is my am related to happy? Okay, and then same goes with happy. How is happy related with I? How is happy related with M? How is happy related to happy? Okay, so basically what I want is, I want to create a table or a matrix which basically explains every impact of every word on every other word. Okay, now I'm talking about word because I'm taking word based tokenization. Ideally it is impact of every token on every other token, and I do want to quantize it because this is just an idea. Okay, this is what I want, but this is an idea. What is this number? How is this higher than the other one? How would I calculate that number? It's all being done by attention. Okay, now we'll just see how it works. So what we do is, for now what we have, for example, is this. We have this, let me just highlight it. We have this, which is a meaning plus contextual embedding layer. Let me just redraw this. Okay, for example, what we have currently is a 512 dimension vector representation of I, 512 dimension representation of M, 512 dimension vector representation of happy. Okay, and now this includes my positional encoding plus meaning. Okay, because I've already captured it using positional encoding and embedding layer and tokenization. So now I have this. What I do as part of attention is, I will try to pass it through neural networks and will create certain weight matrices. So what I'll do is, I'll pass through three different layers. Let me just choose the colors first. I'll use teal color for key, gray color for query, and yellow color for value. Okay, so now I'll just move it down as well. This I'll move a little down so that we could draw the complete thing. Okay, so now we'll make small representation of what actually happens. Okay, so I create a neural network here. Please ignore the diagram. I am bad at drawing a diagram here, but basically I hope you'll understand. Okay, this is a neural network representation. Okay, too much clumsy, but okay, this is a neural representation. Okay, and I will do similar for copy, and I'll paste it here. Then I'll paste one more of this. Okay, let me just select it. I'm just drawing as of now, so I'm taking a little while, but I'm just making it small as well. Let me make the other two also small. It's too big. Okay, so this is my now. Okay, so I have a neural network here for key, I have a neural network here for value, I have a neural network here value. Now I'll explain all this, what is key, query, value, but for now I'm just drawing this like this. So let me take white color, and this basically means this complete thing is being sent to 1, 2, 3 neural networks. Okay, which will then generate another representation of this positional encoding, and meaning is it will generate basically again a 512 dimension vector representation of first word, second word, third word. Same, it will do it for first word, second word, third word. Okay, and then same goes for this one as well. Okay, let me just color it and I'll come back to you. Okay, so now coming back to, I've just colored all this, and I'll just quickly explain you this as well. Now, sorry. I hope it is visible. So now, okay. Now there are 3 neural networks that I created, and those now correspond to a new dimensional representation of those single words. I'll just call this K, Q, V. Now why K? K basically means key, Q basically means query, and V basically means value. Now this concept is taken by database DBMS, database management system, which basically implies that for every key that I will query, I'll get a value, right? From when we query a key, we get a value, correct? So that's the complete idea. To get these values, to get the value for attention majorly, what I want to do is I'll create a key query value combination, which is generated by the word embedding layers themselves when they pass through a key vector. And these weights, I'll just, that's WK. Okay, then there's one weight which is defined by W query, WQ, and the other one which will be defined by WV. Okay, so these key query combinations, this is basically, if this was defined as X, for example this was defined by X, now this key becomes WK of X, this becomes WQ of X, and this becomes WV into value. Okay, so these are basically multiplied, and we get a weight vector representation of these values. Now what we do is, we basically, because these are, now this is what, I'll just write that as well. This is nothing but 3 into 512 dimension vector, 3 cross 512 dimension vector, 3 cross 512. So this is a vectorial representation matrix, 3 by 512 sized matrix. So now what we now that we have these three representations of key query value, what we will do is we will basically will multiply the key and query. Okay, so what we will do is we'll multiply the key and query. And how will we do it? Because now that these both are of 3 cross 512 and this is also 3 cross 512, we cannot multiply both the matrices of the same dimension, right? So what we will do is we'll transpose one of these. So what, I'll just draw it in an explainable way. So what we'll do is we'll take key as it is. Okay, no, let me, yeah, so what I'll do is I'll transpose the key. So my, this becomes this, second one becomes this, third one becomes this. Okay, and then I will send this query which I'm getting from here and will multiply here. So this is now K transpose and this is my query vector. Okay, so and I'll just rewrite it. So in white color I'll just rewrite it. So that's my K transpose now into Q. Okay, that's what I'm doing now. K transpose is what, 3 cross 512, sorry, it's changed to 512 cross 3, 500, and let me just write this above and this below. Okay, so I'll write this is my K transpose, that's my Q, and I'm multiplying this. And why am I able to multiply is because this has become 512 cross 3 and this has become 3 cross 512, and this will now generate a 3 by 3 matrix. Okay, K transpose Q will now generate 3 by 3 matrix. Which now, if I come back and see again, like revise back what we were reading and had a hypothetical understanding, was this: I am happy, and so is I am happy, and these values are now the scores, which basically implies the impact of I on M, I on happy, or M on I, M on happy, like that. So now we have interactions. Now this is not I represented here, it's just to understand, okay, this is how it looks. Okay, so now we have the attention scores. Now this is not how we use the attention scores, because what happens is it's not just a simple way, because what we do is these numbers are up down. So what we do is we balance these numbers, normalize this, because now that we have got, okay, this is what attention scores look like, we'll now try to normalize it in a form that, okay, this could be interpretable. Okay, for now these numbers are not interpretable, because these could be very big number, this could be very small number, something like that. So what we do is this, I'll just write this matrix by, let's say, K transpose Q. Okay, now what we do is we divide it by root of dimension of the matrices, which is for now 512. Okay, now why do I divide it by root dk? It's again a magic number. There's no concept behind this. It's just they when they were designing the complete architecture, we were coming with an idea of attention is all you need. They basically were trying random numbers and somehow this would have come into picture. It's called a magic number because this suits the needs. So okay, so now we have a K transpose Q matrix divided by root of D, which is 512 for now for us. We have this number which is a little balanced, but what we do is, because this could contain negative numbers as well, what we do is we take a softmax of this. Okay, we pass it through a softmax layer. So now we have probabilities of every number. Now the value ranges from 0 to 1. Okay, where bigger number implies bigger impact, smaller number implies smaller impact, and 0 means no impact. Okay, now because of softmax, the sum of all the values will be 1. Okay, because now these are probabilities and hence they are readable. Okay, now after we get this K transpose Q by root dimensional, we multiply it with the value vector. Why do we multiply it with the value vector? The reason for multiplying it with the value vector is basically we have got the attention scores. Now we are multiplying it back with the value vectors to get again. So now what is the dimension of the matrix? 3 by 3, but this is attention scores. So we multiply these attention scores to the value, which basically is, now will get a 3 by 512 matrix, which already previously contained positional encoding, which already contained meaning. Now it captures the impact on every other word, which basically means it captures the context as well. So now this matrix that we have here has meaning already, has now this is 3 cross 512 because we have 3 words, for example. For now we have meaning already, we had order as well because of positional encoding. Now we have something called as context. So we have captured all the 3 basic things of transformers, which is meaning, positional encoding, and context. But this is not it. What happens is we go through a multi-head attention that I'll explain in the second part now.